Alright, today we're going to do a couple different segments, and this first one we're going to start to talk about the mole. Now, the mole is a unit that we use in chemistry. But it's a very odd unit because this unit converts mass to volume, and that's in a gas, to the number of particles. Now these particles could be different number of atoms, it could be different molecules. We're just going to say number of particles. So we're including everything. So a mole is not a fuzzy little animal. The mole we're talking about is a unit. We're going to abbreviate the mole as just a small letter M-O-L, and that's going to stand for mole. Now, the person that first discovered this relationship and discovered the relationship between mass, volume, and number of particles his last name was Avogadro. And he was an early scientist, and he experimented with gases. And what he found is that if you had gases at a constant temperature, which was 0 degrees Celsius, and a constant pressure outside the container, and this would be the air pressure, and that was going to be 1 atmosphere. So basically, at sea level, and the atmosphere is abbreviated ATM. So we have a constant temperature, a constant pressure. If you have a volume of 22 liters, then that amount of gas particles you would have would be a huge number. It's 6.02 times 10 to the 23rd particles of gas. So this basic relationship is what started the idea of the mole, that you could actually look at the volume of a gas and determine how many particles were actually in that volume of gas. Let's take a look at a picture here. Let me pause it. Alright, so what Avogadro found is that it didn't matter what kind of gas he had. He could be using a very light gas like helium. It still took up 22.4 liters of space. Or he could be using a heavy gas like chlorine, and that still took up 22.4 liters. And remember, this is at STP, standard temperature, which is 0 degrees Celsius, and standard pressure, which is at sea level. Okay, so as long as those conditions are true, no matter what gas you have, it's always going to take up 22.4 liters as long as it's at standard temperature, 0 degrees Celsius, and at sea level. Now the next point that follows is that if these set number of particles has a set volume for a gas, well, each of those particles has weight. We know that all atoms have weight. So the mole is also a specific mass of 6.02 times 10 to the 23rd of those particles. So, a specific mass for all these particles. Now, For atoms, all atoms do not have the same mass. So all those elements on the periodic table have different masses. So let's take a look at a picture of the periodic table. And whenever you're looking at a periodic table, you're going to see that there's usually a key, and it'll tell you that what's in the top corner, what the symbol for the element is, what the name of the element is, and down here is the mass. So that's going to be the weight of one atom in a unit called AMU. Well, with the mole, all you have to do is change AMU, gets converted to grams. So if we're looking at iron here, element number 26, its symbol is Fe, the name is iron, and right here is the mass. Now in AMU, that would be the weight of one atom of iron. Well, what we're going to do is we're going to cross off AMU and just change that to grams. So if we weighed out 55.845 grams of iron, we would have 1 mole of iron. Putting these ideas together, we've got a mole is 6.02 times 10 to the 23rd particles. These particles have a mass for a mole based on the type of atoms that make the particles up. So we've got a number of particles, we have a weight of that number of particles, and then finally in a gas, and this is important, this only works for gases only, we can calculate the volume those particles would take up. All right, let's connect this with something that's a little bit more familiar. Let's pretend that atoms are like cars. So let's just pull this truck out here. So you'd agree that the mass of the truck is going to be different than the mass of any of these cars. Each type of car would have its own mass. So we have the weight of one truck. If we had 100 trucks, we just multiply that mass by 100, and that would give us the mass of 100 trucks. Well, if instead of 100, we had erase that out. Instead of 100, we had 6.02 times 10 to the 23rd trucks. That would give us the weight of a mole of trucks. In the same way, if instead of having the trucks, we had, so if instead of trucks, we had this type of car, we'd multiply the weight of that car by 6.02 times 10 to the 23rd, and we would have a mole of that type of car. And I could continue to just move these out. If I had this, the weight of that car, multiply it by 6.02 times 10 to the 23rd, and it would be a mole of hatchbacks. So that's mass. So volume. Volume's a little bit trickier because we have to kind of pretend that our cars follow certain rules. Well, rule number one is that our cars always move. The next rule is that if they collide, they bounce off of things. If they hit the walls of the container, they're going to bounce also. Now they're still going to hit the wall of the container with some force, but instead of crashing, they're just going to bounce right back off. All right, so let's look at volume and the mole. So the volume is going to be the space that's taken up by the particles. Now remember, this is only going to be true in gases. So our cars are going to behave like gases. Like I said, there's 3 rules. They're going to be going at a constant speed. If they hit each other, they're going to bounce off of each other. If they hit a wall, they're going to bounce off the wall and just keep on moving. So you can see I've got some walls drawn in here. There's a wall. Now, the weird thing with this idea is that my cars can actually go any direction. They could go up, they can go down, they can go left, they can go right. They're just bouncing around this container. When they hit the sides of the container, they're going to bounce back. So if I only have this number of cars, it's going to take up a certain number of space. So my cars are basically just driving forward and going until they collide and hit something. Now if I've got more cars, those are going to hit against the sides of my container more frequently. This car here is going to drive and hit. This car here is going to hit. This one may bounce up this way. Remember, these can move in any direction. The more cars I have, the more collisions they're going to have with the wall. And that's going to cause more pressure on the walls of my container. And so my container is going to have to get larger. The more cars I have slamming into the walls of my container, the larger the container is going to need to get, or my container is just going to burst like a balloon that has too many particles in it. So when we're talking about the volume of a gas, what Avogadro discovered is that the volume of a gas at 0 degrees Celsius and sea level will be 22.4 liters. If you have half the number of particles, in the same way that if I had half the number of cars, so if I have half the number of cars, I'm going to have half the number of collisions with the sides of my container, and my container is going to get smaller if it's flexible like a balloon. So basically what he found is that if he had 1/2 a mole, what would the volume be? Well, it would be half a mole, so it would be 11.2 liters if you had that many particles. To summarize this, we've got mass, we have the number of particles, and we have the volume, of course, of a gas at STP. In order to get from one thing to another, we've got to convert. So if we start with the mass, or how much of a substance weighs, we can, using the molar mass, convert to how many particles that would be by using Avogadro's number, 6.02 times 10 to the 23rd. If we're dealing with a gas, and we know the number of particles we have, we want to see how much volume that's going to take up, we can use these conversion factors, the number of particles in a mole, and the volume of 1 mole, to figure out what is the volume of the gas, even if we don't have a full mole of particles, or we've got 2 moles of particles. So this becomes a factor label problem, and I'll show you how to do those in the next video.